All right. So today we're going to talk about memory layout and how it can affect performance, to put it short. And this is not going to be some kind of optimization guide, certainly. There are going to be a few tips in here of things you can certainly try, right? And that you probably should think about. And I'm going to try to keep it to things that are simply, this is a good idea, and so on. This is a good idea to at least try to see. And we're going to go over some of the intuition you can have for why are these things faster? And what is it that actually makes them faster and so on. So let's jump to the code here where we have our humble particle, right? And so we have a particle here with x, y, and z, vx, vy, vz, mass, and so on. The order of these actually doesn't necessarily matter. Certainly you could just have vx, vy, and vz up here if you wanted to. They're ordered like this only because it kind of looks neat. We have x's, y's, and z's. We have vx, vy, vz, etc. We also have the mass here. And so I want to go over the actual calculation that we're going to be doing. So we have our particle count here, which we calculate from the size that comes in. We start at a size of 0.1 and we multiply by 1,000,000, right? So these sizes go up to 100, so the highest is 100 million particles that we are calculating. A very simple calculation for. We set some, first of all, we make our particles here, right? The particle count, we delete that, doesn't necessarily matter. We then set some values for these to have by default for every particle. And then we do a calculation here that says basically add pvx, right? The vx we have to x, add pvy to y, etc. Right? Very simple calculation, nothing super interesting about this. Mostly straightforward arithmetic, right? And this is going to remain the same for all of these tests. Fundamentally, the calculation is the same. So what happens when we actually run this? We have only our normal case here. Actually, let me clear this. We can run this here. So here we have, this could be seen as our kind of baseline or whatever, right? I want to show this here now because obviously we can see here that there is a difference in size, usage or whatever here. And we can see that there's a stark kind of difference here in once you go above a certain amount, certainly you're not expecting to do this, for example, in one frame, this thing here, right? So this 20 here basically disqualifies this entirely from being used, for example, per frame in a game, right? So we can see here that 10 million particles like this would just not work, period, right? And here for this 220 ms, we're so far beyond that is obviously impossible with this structure and this calculation. So clearly this will not work for that kind of scenario, right? This would only work for, hey, I want to generate some kind of image right now or something, right? And so that's our normal case, right? I want to show one that should prove no different, really. We have our particle arrays here. And this is a language feature here that we can use in Odin, that when we have an array of size 3 like this, we can use .x and .y and .z, and they will refer to the 0th and 1st and 2nd index, and so on. This applies to both our velocity and our position. So when we use this, right, we can see here, we make our particle arrays just as we did before, but we can use p position.x, p position.y, etc., p velocity x, velocity y, velocity c, and so on. And our calculation here looks basically the same, p position x plus, etc., etc. There should be no real difference between these. I have seen some variance, I will say, and the variance is much higher when we're using OBS as well for some reason. But we can see here that broadly speaking, there should be no real difference. We can see some of them are faster, some of them are slower, but there's no real difference, right? And we get our .x syntax and so on from just having these types of arrays, right? And so that's basically fine, right? This really should be a null difference in reality. There shouldn't be anything different about these two. and so on. And I wanted to show that because it's actually a neat feature, this in Odin, and I think it's worth using a lot of the time. However, what are some things that actually impact performance though, right? I want to show this one here. Let's see here if we can just draw out a line here. And I want to show sort of what actually happens in an array when we have these things. Let's say we have this here, right? And we're going to say mass here, over here. That's fine. When an array is being read by the processor for, computation, right? We depend on memory, right? So we're going to read from the memory that we've allocated and so on and so forth. What actually happens is it's going to read a cache line worth of data. Cache lines, I guess they can be variable 64, 128 bytes or something. I don't actually remember. Point is that there is a size, right? And much like that, we also have cache sizes, right? So the L1 cache is a certain size, and this can depend on the processor or whatever. And the L2, L3, and so on, right? I guess the L1 is pretty uniform as well. But the point is there are different sizes to these things, right? And so let's imagine here that this is, let's say this is L1, right? Or a cache line or whatever. It's a sized, there's a strict sizing here, right? Something fits or it doesn't fit. When the processor is reading our array, it will just say, oh, I'm gonna start processing this. We need X because we're obviously calculating a new X and so on. And we need VX and so on. And when it reads this X, it's actually going to read all of this data, right? Up to a certain point, to here, for example. And so it can work very fast with this data that it's loaded now, right? X, Y, and Z up to this point here, right? What if we just said, hey, I'm going to just remove mass here, right? Now suddenly we can see very clearly that, hey, I can fit more of these, right? Potentially we can right? So we actually fit X, Y, and Z and VX now. In the same space we actually had, less in before. So that's what we're doing here with particle no mass. We're going to be saying here that we have V, Y, Z, or X, Y, Z, VX, V, Y, VZ, etc. But we don't have any mass. So if we look here at run no mass, the code otherwise looks the same. We simply don't initialize mass, but that was never timed, so it didn't really factor into the timing of any of this, right? The calculation here remains the same as our previous thing as well. I'm going to comment out arrays here because we don't need this. This is effectively a null difference, or should be. And so here we're going to be seeing that there is a difference, certainly, right? One of these is actually higher. It simply shouldn't be. Again, this is variance, I think, caused by OBS, generally speaking. We will see if we run these multiple times and so on, there is a difference. And that difference is simply because we can fill the cache line with data we actually need only. We can fill L1 cache with data we only need, right? Only the data we need, sorry, and so on. We can also see we're using less memory for this calculation as well. So generally speaking, this is going to be faster, right? By some amount, right? And this amount, to be clear, we only have 32 bits more. What if, like in many systems, we also have name and string here? I would bet here that we're going to be seeing a larger difference, right? Remember, normal now has much more data, right? And this is exacerbating this issue, right? This is basically now making it so that we are filling even less. We're filling the cache line with less information that we need, right? There's more information we don't need in there. And we are seeing the effects of this here, right? Significantly higher processing times. And only from having just data in a structure, right? And of course this happens to everyone mostly, right? Unless they're kind of thinking about this ahead of time and so on. So the general lesson there is simply have only the data that you need for a certain calculation in the arrays that you're processing, right? And so this is a good idea to think about, right? This is a good guideline to a large degree, right? Try to minimize, if you can, the amount of data that is involved in these things that shouldn't be there, or we don't want loaded into the cache or anywhere else, because it simply is not useful for the calculation we're doing. We're going to leave that there. So that was no mass, right? There's an alternative way to also kind of rethink a lot of this. Here we have particle SOA. And I want to explain SOA here. This stands for structure of arrays. And I'm saying SOA here because it is a, let's say, established, let's say, keyword. If you search for SOA and AOS, you will find these. So what is AOS? AOS is array of structures, right? This is an array of structures. Obviously under the hood, there's a data pointer here that points to just an array of particles. That particle is just a structure. It's a sequence of values, exactly what we saw before, right? X, Y, and Z, etc. It's this array, right? And so structure of arrays is instead having multiple different arrays for each attribute, right? This might seem a little bit odd, but we're going to go over kind of why that makes sense. You might also be wondering here, what is this pointy thing, right? And let's go to the Odin website. Let's see here if we can find this. A multi-pointer, right? And so I want to stress here what it's saying, a C-like pointer which act like arrays. Because if you didn't know, when you pass an array to a function and so on, it basically decays into a pointer and so on. This pointer can, you know, be used certain ways and so on. In Odin, we have this multi-pointer to basically allow you to use this as effectively a C array. We can index into it and so on and so forth, right? It does not contain any length, right? Because it is effectively a C array, right? And you shouldn't use this in your code, I would say. You should use this in code that needs to interop with C and so on. The only reason we're actually using this here is because basically this is what a certain keyword will expand the structure into, and we're going to be looking at that a little bit later. So the important part here is we have our X's, we have our Y's, we have our Z's, and so on and so forth. And these are all in different arrays, right? In this particular case, we actually have elected to have them in completely separate memory positions. These are going to be, they're going to be allocated separately. So there's no contiguous structure here where the Y's follows the X's and so on and so forth, right? We can do that, but that's not what we're doing here. Instead, we have just our X's, we have our Y's, we have our Z's, and so on. They're completely separate arrays and so on. And mass is still here. Let's remember that. Here we have run arrays SOA, which is going to first establish the particle count as usual. And then we have our particle SOA object here. And this is just on the stack. There's no actual heap allocation happening there. But then we fill in every attribute here, right? X's, Y's, Z's, VX's, VY's, VZ's, etc. with a new array. right? And we're allocating these as multi-pointers and so on, right? So we make that amount of entries. We also free them here. Nothing super interesting going on here. We also set a length here, because remember, all of these have the same length. That is actually why it's more efficient to use a multi-pointer here. It does not store length. If we had slices here, they would also store lengths. So we would be duplicating that information over and over. That's not needed. And so we have the slice here, F32s, particle count, etc. Right? These are not now all separate. We set our values here, just as we did before. They are now just indices into an array, obviously, right? We're indexing into that array, looping up to particles length, and so on. Setting these values. Here we have this no bounds check. I honestly don't know that it made a difference in this particular case. It doesn't matter so much. Now we have this, we set particles X indexing into that. We set that to add Vx, etc. Right? Nothing incredibly interesting about this at all at the moment, right? And so here, this calculation is not actually correct. Let me just find that calculation. We're gonna copy this one because I happen to know that it's not misleading as that one is. Run raise, so here we go. There you go. So let's run this. We have arrays SOA here, right? Now we're gonna have normal, we're gonna have no mass, and arrays SOA. So let me save that and then run it. That would help. So we're gonna see normal, we're gonna see the no mass, etc., etc. And we're gonna see here that there's a distinct difference. No variance here can really work against the fact that certainly there's a difference in speed here, right? Now, why would that be, right? We have spread out all of these things in memory to some extent, right? We have different arrays for different things, right? But there's a thing here that happens when the processor is trying to read this information. So let's look kind of at how this works. So for this calculation down here, right? When we are adding to x's here, right? All of those x's are in line, right? They're just x, etc., right? All the vx's are in a line, just a bunch of vx's, right? You can fit a lot of these into one cache line. You can fit a lot of them into L1, L2, L3, etc., right? But there's also one more, let's say, important thing going on here. First of all, we're setting up a scenario where if we were to do something with x's and vx's, obviously we can now fill entire cache lines with these values. This is essentially a guarantee, right? So we've already gained that, right? But what actually happens is that Odin and or LLVM also can recognize here that we can do something called SIMD. And SIMD is single instruction, multiple data, right? What this actually means is that we can load multiple x's and multiple vx's into specific registers and then effectively call batch calculation operations on those values, right? So we can end up loading instead 8 of these F32 values, these float 32s and so on, into these registers and then do a bunch of those calculations at once. On top of that, there's also something here that's going on that the processor can see and that an optimizer can see as well, right? Which is a very uniform access pattern, which is easier to actually get when you have this kind of layout. So we can see here that we are using x's and then we're loading x's effectively, right? And then we're loading vx's as well, right? we're loading y's and then we're loading vy's, etc. Right? This kind of uniform access pattern can effectively make it so that the processor knows which things to prefetch. And so prefetching would be the processor understanding that, oh, I know you're gonna need this data, so I can load a bunch of that data. That kind of situation is easier for the optimizer, for the processor to actually create when we actually have these in separate, separate buckets, let's say. And the bucket only contains that data. It doesn't contain maybe some other data. It doesn't contain nil or that data or whatever, right? It contains that data specifically, right? And so in this type of scenario, we have set up effectively the processor to be able to do what it does best in the best way, in somewhat good way. I don't know that this is the best, but it is certainly much better still, right? And now you might be thinking, well, I'm not entirely sure. I think some of this, honestly, it looks kind of tedious. Now I have to rethink all of my structures as just being these arrays. And even worse, we have these multi-pointers. And you don't have to, if we're being completely honest. It's not going to impact the stuff that much. But, there's a certain cost here because we are effectively reimagining what the actual structure is. But there is a keyword in Odin, hash SOA. And what hash SOA does is we can take some array or slice or dynamic array, for example, and a regular structure. And what's going to actually happen, in fact, is we're going to get the same thing we looked at just now. And so let's see here. We have this auto SOA here. We're going to comment out normal here because, yeah. Let's see here. When we run these three, we run no mass, array SOA, and auto SOA. We're going to run this here and see that there is a difference here. A general difference that we maintain, in fact, right? We can see here that auto SOA, with just a minor difference in the lowest, and the lowest is especially, I think, affected by OBS running. So I wouldn't take that one too seriously at the moment, to be honest. We can see here that, if anything, it does the same or is slightly faster than array SOA. So auto SOA, right, is effectively just the version here where I've just said, hey, make this SOA, right? And that has yielded effectively the same as when I did this manually, right? And this gets better. So let's look at what is auto SOA actually, right? If I go here, and we can hear, for example, here we can actually say particle auto SOA. This is a type I have defined, and that is this type, right? And we can see here that, okay, we now say particle count here, and then we have this make SOA, right? And note here, I can't actually say make. I have to do make SOA. Not a huge difference though, but we can make our auto SOA structure here with our particle count. And then we say, hey, for every, we just do this reset or this value set, right? P.x is 1, P.y is 2, etc. This looks like our normal code, right? And here we have the timed section. Note here, I'm not mentioning indices at all. There's no index. I'm just saying px is plus equals pvx. But all of this now exists in separate arrays, right? And so this code is, it doesn't actually look different, right? And that is, in some ways, you could argue that it's maybe there's a cost here, right? It looks no different, but it certainly behaves differently. But in this particular case, it certainly behaves better, right? And so note though, yeah, this is effectively, we have the same code we had in our normal example, but we now get just better output, right? We have now effectively we've shaved off considerable time in some of these cases. And I would say the difference here is actually, the difference is smaller now than when I wasn't running OBS, for example. But it's certainly, there's a difference. There's a real difference between these two, right? And in this particular case here, all we actually had to do was add the SOA keyword and use make SOA, right? And also delete SOA. Actually, let's see here. No, you need to delete SOA. And if you think about it, this is because it has to understand that you want to free or whatever, all of these separate arrays that are going to exist, right? But other than that, Odin here is basically managing effectively everything for you, right? And the splitting up of all of these things has allowed effectively a different access pattern, right? The processor can now work more efficiently with prefetching. The compiler can see that you're doing an operation that we can use SIMD for. And because all of these are now neatly in lines, right, different lines, it has no problem just loading a bunch of them into these SIMD registers and doing SIMD operations to calculate these values, right? Many at once instead of one at a time, and so on. So this is a very reasonably engineering time cheap way of saying, hey, let's look at what we can do here with SOA instead of AOS, right? Let's use a different layout here, split things out if we have these bulk type operations that don't need a bunch of these values and so on in different operations, right? Because we can see here mass is equally here, but it doesn't factor in here. So it's never loaded into any kind of, memory. It's never loaded into cache on the processor. It's never actually interacted with. So mass does not disrupt any of these calculations. And so yeah, the takeaway from this video, I guess, should be that memory layout can certainly affect a lot of your computations, right? And one of the things you should think about in general is don't load data that you don't need for a calculation, because it will affect your processor's ability to optimize around these things, right? And also having many of the same thing in one line is going to generally be better and easier for the processor to do what it needs to do with, and so on. So yeah, again, this was not an optimization guide. I want to make that clear. These are just some of the things that you can take a look at in order to see if you can make your calculations faster, and so on. And they are very useful for these type of bulk operations. And in general, thinking in bulk is, I would say, a good idea. If something is worth doing, it's worth doing for a lot of things at the same time, because doing the same operation on many things, again, that's what makes this faster, right? Having many of the same things in one place so we can all, we can load them all and so on, that is what makes this faster, right? And so on. So yeah, I wanted to go over this. And again, the takeaway here is that you can use the SOA keyword, right? #SOA with some slice type here in order to do these things. And as I showed before, you can also actually just do this here. You don't have to define a type for this if you don't want to, right? It is entirely possible to just say this, right? So in effect, the diff here would be make SOA, make a SOA version of the thing you want to do. And then we have our count. Use delete SOA instead, and so on. And then we can effectively, the rest of the code remains the same, right? And I think that this is a very neat thing. And I think it's worth, experimenting with, certainly in most cases. And so, yeah, that was it for this episode. If you like the episodes, subscribe, comment, like the videos. And I would love to hear your opinions in general on the Odin learning series or the projects that we're doing in general. Also, jump in the Discord, hang out and just be one with the community, so to speak. I would love to hear from all of you. So, with all of that said, have a nice day and ciao.